In this video, we'll see what happens when we multiply a matrix with its adjoint. In the previous video, we found the adjoint of this matrix 1, 3, 3, 1, 4, 3, 1, 3, 4. To find the adjoint, we had to find cofactors, and to find cofactors, we had to find minors. So we found all 9 minors, and then we found cofactors, and then we took the transpose to get the adjoint. These were the minors. And if you put the minors in a matrix, this is what we get. Now, if you flip signs of these 4, we'll get cofactors. And if we take the transpose, we'll get the adjoint. Now let's multiply the original matrix with its adjoint. We have 1, 3, 3, 1, 4, 3, 1, 3, 4. And the adjoint is 7 minus 3 minus 3, minus 1, 1, 0, minus 1, 0, and 1. Let's multiply. This is what we get. We get 1 times 7, 7, minus 3, minus 3. That's our first element, 7 minus 3 minus 3. Then we have minus 3 plus 3 plus 0. Then we have minus 3 plus 0 plus 3. So this is the first row. Then we have 7 minus 4 minus 3. This is the first element of the second row. Then we have minus 3 plus 4 plus 0. Then we have minus 3 plus 0 plus 3. Here we have 7 minus 3 minus 4. Here we have minus 3 plus 3 plus 0. This one is, the last one is minus 3 plus 0 plus 4. So let's simplify. This becomes 7 minus 6, that's 1. Minus 3 plus 3 is 0. 0 plus 0 is 0. Here as well we get a 0. Minus 3 plus 3, a 0. This one is 7 minus 4, that's 3. 3 minus 3 is 0. Again a 0. Minus 3 plus 4, that's 1. 1 plus 0 is 1. Then we have minus 3 plus 3, that's again 0. A lot of zeros. Then we have 7 minus 7, again a 0. Minus 3 plus 3, again a 0. Minus 3 plus 4, and finally we have 1. This is the identity matrix. So what this means is if we multiply this particular matrix with its adjoint, we actually get an identity matrix. Now I wonder, why would this be happening? The determinant of an identity matrix is 1. Let's also find the determinant of this original matrix. 1, 3, 3, 1, 4, 3, 1, 3, 4. Let's see if we can get any clues from here. This is the determinant. We have 1 times 4 times 4, 16, minus 3 times 3, 9. So 16 minus 9, minus 3 times 4 minus 3, plus 3 times 3 minus 4. So this becomes 7 minus 3 plus 3 times minus 1, again minus 3. So that's 7 minus 6, that's equal to 1. The determinant of this matrix was also equal to 1. Let's try this on one more matrix. We have another matrix A. This is 1, minus 1, 2, 3, 0, minus 2, and 1, 0, 3. Let's find the adjoint of this matrix and then multiply both of them. Pause the video, try this on your own. Okay, let's do this together. Before we begin, let's quickly find the determinant of this matrix as well. The determinant of A, that's equal to 1 times 0 minus 0 minus minus 1 times 9 minus minus 2 plus 2 times 0 minus 0. So this is 0, this is 0, this becomes 9 plus 2, that's 11. 11 times 2 negative signs, so that's plus 1, so 11 times 1. So determinant of A, that's equal to 11. All right. Now let's find minors and then cofactors and then the adjoint. So we'll have minors, cofactors, and adjoint. For minors, this is what we have. On top left, we have 0 minus 0, that's 0. Here we have 9 minus minus 2, that's 9 plus 2, that's 11. Top right, we have 0 minus 0, again a 0. This one becomes minus 3 minus 0, so that's minus 3. In the middle, we have 3 minus 2, that's 1. Here we have 0 minus minus 1, that's 1. Bottom left, we have minus 1 minus 2, that's 2. 2 minus 0, that's 2. Here we have minus 2 minus 6, that's minus 8. Bottom right, we have 0 minus minus 3, that's going to be 3. So that's our minors. For cofactors, we'll flip these 4 signs, 11, minus 3, minus 8, and 1. We'll get the matrix with cofactors as 0, minus 1, 0, 3, 1, minus 1, 2, 8, 3. We flipped all 4 signs. Now let's take the transpose to get the adjoint. So this is what we have: 0, minus 1, 0, 3, 1, minus 1, 2, 8, and 3. Now we have the original matrix A and we have its adjoint. Now let's multiply. Multiplying A with its adjoint, this is what we have: 1, minus 1, 2, 3, 0, minus 2, 1, 0, 3, multiplied by 0, 3, 2, minus 11, 1, 8, 0, minus 1, 3. So this is what we get. We have 1 times 0 is 0, minus 1 times minus 11, that's 11, 2 times 0 is 0. So that's 0 plus 11 plus 0. Note that 11 is interesting because mod of A is also 11. Then we have 3 minus 1 minus 2. That's 3 minus 1 minus 2. Then we have 2 minus 8 plus 6. 2 minus 8 plus 6. Here we have 0 plus 0 plus 0. A 0 here. In the middle we have 3 times 3, 9 plus 0 minus 2 minus 1, that's 2. So 9 plus 0 plus 2. Here we have 6 plus 0 minus 6. Bottom left we have 0 plus 0 plus 0, that's 0. Here we have 3 plus 0 minus 3. Bottom right we have 2 plus 0 plus 9. 2 plus 0 plus 9. So let's simplify. This is 11. This is also 11, 9 plus 2. This is also 11, 2 plus 9. What about the other elements? This one is 3 minus 1 minus 2, that's 0. 2 plus 6 is 8, 8 minus 8 is 0. 6 minus 6 is 0. 3 minus 3 is 0. And these two have all zeros to begin with. So this means all other elements are 0. A multiplied by adjoint of A actually gives us 11, 0, 0, 0, 11, 0, 0, 0, 11, which we can rewrite as 11 times the identity matrix. Now, do you notice what's happening? Pause the video. Think about what's the relationship between A, adjoint of A, determinant of A, and the identity matrix. All right. What we're actually getting is not A times adjoint of A equals to identity matrix. What we have is A times adjoint of A, this product, that's equal to the determinant of A times the identity matrix. In the previous problem, we were getting the identity matrix because the determinant was in fact 1. In this case, it's equal to 11, which is why we're getting this matrix, 11 times the identity matrix. So what we have is A times adjoint of A, that's equal to determinant of A times identity matrix. And this works the other way around as well. You can pause the video and try it yourself. If you multiply adjoint of A with A, if you flip this order, you would still get the same answer. You would still get 11 times I, or determinant of A times the identity matrix. This is the solution on the screen. You can pause and check for yourself. So if you multiply A times adjoint of A or adjoint of A times A, in both cases, you'll get determinant of A times the identity matrix. So this is the property that we have discovered through these examples. Now we don't have a proof for this, but we can develop intuition by taking some variable elements. Let's do this. We have the matrix A, a 3 by 3 matrix with these elements, A11 to A33. And let's say the adjoint matrix is this one. The elements are all cofactors, A11, 1, 2, 1, 3. And because we have taken transpose, we have 1, 1, 1, 2, 1, 3 as the first column. So this is A and this is adjoint of A. Let's try multiplying. If you multiply A with adjoint of A, this is what we have. Now at first it looks scary, but if we look closely, if we look at individual elements, we'll see the pattern. If you want to pause the video and try to find the pattern yourself, feel free to do that. Okay, let's do this together. Let's look at the first element. We have A11 times A11 plus A12 times A12 plus A13 times A13. This looks familiar. This is actually equal to the determinant of A. We have seen this in one of our previous videos. We also have another element, A2121, A2222, A2323. This is also equal to the determinant. Here we are opening using the first row. Here we are opening using the second row. Similarly, this element, A31, A31, A32, A32, and A33, A33. This is us opening the determinant using the third row. All three of them are equal to the determinant of A. What about the rest of the elements? Rest of the 6. Let's look at them. This is 1, 1, but this is 2, 1. This is 1, 2, but this is 2, 2. This is 1, 3, but this is 2, 3. So we're multiplying the elements with the cofactors of a different row. And we have also seen that this will always give 0. And that's the case for all other elements. We are multiplying using different cofactors from different rows. So all 6 of these values will become 0 and all 3 of these values will become equal to the determinant of A. So this is what we're getting. We're getting a matrix with these 3 values equal to the determinant of A and the rest of the values equal to 0. And that's why we can take the determinant of A common, and this becomes determinant of A times the identity matrix. So that's what's going on here.